So now we're going to look at some more rules. These rules really have their counterparts in the rules for differentiation. And so when we're looking at integration, I don't think these will come as a big surprise to you. So rule number 3 is the constant multiple rule, which says that the integral of k times the function f of x is equal to k times the integral of f of x. It's sort of like with limits. Remember, you can take the constant factors out. Same thing here. If it's a constant factor, you can pull it out, like this, the 5 in this example. You cannot pull variables outside the integral unless you really know what you're doing. Anyway, let's take a look at this one. We've got the integral of 5x cubed with respect to x. So I am going to pull that 5 out. And I'm going to integrate x cubed with respect to x. And I'm getting 5/4 x to the 4th plus c. Now let's look at integration involving trig functions. We know the derivative of each trig function, and we can turn those differentiation rules around to get integration rules. So for instance, the integral of cosine x, we need to know what function has the cosine x as its derivative. What do you differentiate to get the cosine of x? You differentiate the sine of x. And what do you differentiate to get the sine of x? Well, if you differentiate cosine, you get negative sine of x, so it's the wrong S-I-G-N. So what you really need is negative cosine x plus c. If you differentiate negative cosine x, you would get negative of the negative of sine x, which would be sine x. And I hope you remember what you differentiate to get the secant of x. That's tangent x. And you differentiate the secant of x to get secant x tangent x. So the integral of secant x tangent x is secant x. Cosecant squared, that's going to be negative cotangent x plus c. And cosecant x cotangent x, that's going to be negative cosecant x plus c. Notice that when you integrate and get a function that starts with CO, cosine, cotangent, cosecant, there's always a negative in front. So our next topic is solving differential equations. A differential equation is an equation that involves derivatives or differentials. And here are some examples of differential equations. The first one has the derivative of y with respect to x equals y squared sine x. The second one has a derivative, f prime of x equals 2x plus 1. The third one has a first derivative and a second derivative in it. And I probably ought to change this number 4. dy plus y equals the quantity x squared plus y squared times dx. That one has differentials rather than derivatives. Okay, so by solving a differential equation, what we mean is finding an explicit expression for y or f of x in terms of x. So, for instance, just finding some function that you can put in for y or f of x, and it makes the differential equation true. So, for instance, let's show that y equals 1 over 1 plus cosine x is a solution to the differential equation dy over dx equals y squared sine x. All right. So, our proposed solution to this differential equation is 1 over 1 plus cosine x. And what we need to do is show that that function satisfies the differential equation. So what do? Well, looking at the differential equation, we've got what we need to do is come up with an expression for the left side and an expression for the right side and show that they're equal. So the left side is dy dx. So given that y equals 1 over the quantity 1 plus cosine x, what would dy dx be? What would the derivative be? Well, let's rewrite y as 1 plus cosine x to the negative 1. That will help make the differentiation a little bit easier. All right, so dy over dx will be negative 1 times 1 plus cosine x to the negative 2, and then we need to multiply by the derivative of what's inside. The derivative of 1 is 0. The derivative of cosine x is negative sine x. And I'm going to rewrite that as negative 1 over the square of 1 plus cosine x, and then multiply that by the negative sine x, so that it's really just sine x over 1 plus the cosine of x, and that's squared. So that's the left-hand side of the differential equation. I'm going to put LHS for left-hand side. Now, what would the right-hand side be? Well, the right-hand side would be y squared times sine x. Well, y is 1 over 1 plus cosine x. So the right-hand side is y squared times sine x. And remember, what we're using for y is 1 over 1 plus cosine x. We'll square that and multiply it by sine x. And if you combine everything and simplify, that turns into sine x over the square of the quantity 1 plus cosine x, which is exactly what we have up here. So the left-hand side equals the right-hand side. So this really is a solution to this differential equation. All right, so this was showing that what I gave you really is a solution, but it doesn't show you how I found that solution, and that's really beyond the scope of this course at this point. In a few more sections we'll be able to do this, I think. Yeah, all right. So let's do one that we do have the background for, and that's this one. Solve the differential equation f prime of x equals 2x plus 1. So by solving this, what we mean is find f of x. Well, you've got the derivative, you need to find the original function. So f of x is going to be the antiderivative of 2x plus 1 with respect to x. And you can integrate this term by term. You can integrate the 2x separately from the 1. And if you want, when you're integrating the 2x, you can pull the 2 outside. I think I'm not going to do all that. I'm just going to do the following. I'm going to raise the power on the x by 1, so we've got 2x squared, and now I need to divide by the new power, which is 2. Now, what would you differentiate to get 1? If that's not any help. You can also think of 1 as x to the 0 power. And if it's x to the 0 power, you'd add 1 to the power, divide by the new power. Throw on a plus c. And let's clean it up a little bit. And that looks to be our solution. So, is f prime of x actually equal to 2x plus 1? Well, if you differentiate, you get 2x plus 1. Looks like it's right. Okay. So this solution that we just found contains an unspecified constant c. That kind of solution is called a general solution to the differential equation if it's got that plus c in it. We don't know, we don't have enough information to solve for c, and so what we've really got at this point is just a whole family of functions which are solutions to that differential equation. If we add in more requirements, then we can perhaps solve for c. And so, to obtain a specific value of the constant and obtain what is called a particular solution, we need the value of the function f of x for a specific value of x. And that kind of value is called an initial condition. So solve the differential equation f prime of x equals 2x plus 1 with the initial condition that f of 2 equals negative 3. We already know from the work we did earlier that f of x equals x squared plus x plus c. So, we know that f of 2 is supposed to be negative 3, right? But according to this, according to our knowledge of f, what is f of 2? F of 2 would be 2 squared plus 2 plus c, which I think is 6 plus c. Alright, so we're supposed to, when we plug in a 2, we get 6 plus c. We're supposed to get negative 3. Therefore, these things must be equal. 6 plus c equals a negative 3. Solve for c. I think we get c equals negative 9. In that case, f of x is x squared plus x minus 9. That's a particular solution. We solved the differential equation and we got a solution. We got a solution which we got a single solution, one that meets this condition as well as this initial condition.